Most of us do it. It's just a standard part of the management process, but there's so many things in there that are not made clear to people. In fact, they make very little clear. You'll get a soil test and they'll give you some abbreviations like CEC and pH and some of the stuff we'll talk about today, but they don't really explain what that means. And they'll give you a number. So that's what this talk is about today. What do those things mean? What is hidden in that information? And as you'll see, there is a lot of information in just the first few lines of the soil test if you know how to read it and know how to interpret it. Okay, the first 3 lines of a standard soil test, and this will vary a little bit by the type of presentation you're getting from the soil test firm, but most of them are going to have, the first line will say CEC, and again, it's abbreviation, and they'll give you a number, okay? And then the second one will be pH with a little p and a big H, and then usually the third line is buffer pH. And again, there's very little explanation, if any. Some of the better soil test forms, you'll turn it over and they'll have an explanation on the back, but just a description of what that term means, what the abbreviation means. They don't really tell you anything about the science behind it. Let's start with CEC, because to understand pH, we're going to have to understand CEC. What is that? Okay, CEC is an abbreviation for cation exchange capacity. And if you've got a good soil test form where they give you some definitions, you turn it over, it'll say it's the ability to exchange cations. All right, that's good if you've had a background in soil chemistry, had a soils course in college or something. But to a lot of people, that doesn't mean much. That's a little bit like a foreign language. So I got a CEC, and I got a number, but what does that mean? Is that high? Is that low? Is that good? Is that bad? All right, let's start with the cations. Okay, to understand cation exchange capacity, we need to know what cations are. The cations are a series of positively charged elements that are of importance to us from a soil chemical situation. Okay, there's many cations that are in the soil. Some are very important to us from a nutritional standpoint, and those are the ones that we concentrate on in the soil test. Now, one of those is hydrogen, and it's abbreviated with an H, and you might notice that up here it's got a single plus sign on it. That is a positive charge. And that, first of all, is what a cation is. A cation is a positively charged element in the soil. There are also anions. If you're familiar with phosphorus, phosphorus exists as an anion. Nitrate is an anion. They have a negative charge, but there are many things that have a positive electrical charge, and hydrogen is one of them. Hydrogen has a single plus charge on it. You'll notice that some of the others have 2. We refer to that as monovalent. The valency is the charge, 1 charge, or divalent, 2 charges. And whether it's got 1 charge or 2 charges makes a difference to you, as you'll see when we talk about the modification of pH. Okay, so hydrogen. Hydrogen is a cation. Now, it's not one we normally think about. You don't, you put on N, nitrogen, P, phosphorus, K, potassium. Hydrogen, where does that come in? But as you'll see, hydrogen plays a very important role in the soil, and it is something that we definitely measure and that we are interested in. So, hydrogen is a cation. Calcium. Calcium is a very important cation. It's a very important nutrient. It is involved in cell structure, a lot of other chemical reactions in the plant. Usually we have enough calcium there. There are situations where you can have a calcium deficiency, but you've got to have enough there for the plant to function. It has 2 of these positive charges. It's a divalent cation. Positively charged element has 2 positive charges on it. Magnesium is the third one, and it is a very important element from a nutritional standpoint. If you break down the chlorophyll molecule right dead center at the middle of chlorophyll, you're going to have magnesium. It's chlorophyll that gives the plant its green color. It's chlorophyll that allows the plant to undergo photosynthesis and produce carbohydrates and to have proper root growth and all these other functions in the plant. So magnesium is key to the development of the plant. Now, usually we have enough there, but there are situations where you can have a magnesium deficiency. So it's one of the things that we measure when we're measuring a soil test. The third one is potassium. It's abbreviated with a K, and it has a single positive charge. Notice 1 positive charge versus 2 positive charges. Single positive charge. Very important nutrient element. It's one of the big three, N, P, and K. K is potassium. Very important from a nutritional standpoint. And then finally, sodium. Okay, now sodium is not an essential element for most plants. In fact, it is a toxin to most plants, as sodium can kill plants very easily. But it is a very important one that shows up in the soil. And it is a cation. It's got a single positive charge on it. And as we'll talk about a little bit later, the fact that it has a single positive charge, calcium has two positive charges, makes a pretty big difference to us in the soil. Where does the sodium come from? We've got ice here, and they're putting salt on the streets, most likely, to melt the ice. So you get that on the grass around the curbs. You can have aquifers that have a lot of sodium in it. People who live around the ocean, they get saltwater intrusion, and that's sodium salt. So sodium plays some very important roles too. So these are the cations. What is cation exchange capacity? Again, it is the ability to exchange these cations in the soil. The soil particles, the clay and the humus, or the organic matter, have a series of negative electrical charges on it. And that's what those are minus signs up there. Just like the cation has a positive sign, the soil particles have negative electrical signs. Now, you all played with magnets when you were little. And you know that if you take a north pole and a north pole and you push it together, they're going to push apart. It doesn't work. And if you take a south pole and a south pole, you push them together, it doesn't work. But if you take a north pole, get it close to a south pole, they're going to bond. These electrical charges are very similar to magnets. They can attract each other, or they can repel each other. Two positive charges repel. If I have a calcium and a magnesium and I try to push them together, it doesn't work. They're going to push apart. And if I have two negative charges, if I have nitrate in the soil, it'll slide right by these negative signs on the soil because they repel. However, if I have a positive charge that gets close to a negative charge, they will attract. And that is what cation exchange capacity is. It is the capacity of the soil to hold these cations in place. So when we're measuring cation exchange capacity, we're measuring the number of these electrical charges. And as you'll see in a minute, that number is really, really big. So there's a lot of these in the soil. But they're very important to us because those negative charges hold the cations in place. The calcium, the potassium, the hydrogen, ammonium is another one I didn't mention has a positive charge. They can be held on the cation exchange site, and they can exchange with the root system. And this is the way the root system picks up these nutrient elements that it needs for proper growth of the plant. Okay, so what do those numbers mean when you pick up a soil test form? Again, they're going to abbreviate it, and they're not going to explain it. They're going to say, here's the CEC, and here is a number. Okay, and what does that number mean? All right, it varies a lot by soil type. Notice that a sand has a very low cation exchange capacity. 1, 2, I'll often see on soil tests that I'm looking at from different parts of the country, particularly a new sand construction, like a new sand sports field, it'll be 0.5 or 0.8. Now that's an incredibly low cation exchange capacity. If you look at the top of the column up there, where they list the cation exchange capacity, they'll tell you that it's MEQs per 100 Gs. Okay, and again, they're not going to tell you what that means, but let's look at that. MEQ stands for milliequivalent, and it's a chemical term that I'll tell you a little bit more about in a minute, but it's a chemical term. What we're doing is measuring the number of these electrical sites. 100 Gs is 100 grams of soil. There are 454 grams of soil in a pound, so 100 grams is about a cup of soil. So we're measuring the number of these electrical sites, the number of these negative sites that can hold a cation in place in about a cup of soil when we do this. Okay, again, a sand is going to be very low. Sands have very low cation exchange capacity. Sands, just because of their structure, are not going to be able to hold as many of the cations in place as would a heavier soil, like a clay loam soil. So they're going to have nutritional problems. And a lot of times in the grow-in process with a sand-based system, particularly a new sand-based sports field, you're going to have a deficiency in some of the cations. It can be potassium. Magnesium is often the case. If you get chlorosis in a new field, and you're pushing it with nitrogen and it should be getting greener and it gets yellower, that's probably a magnesium deficiency. And the reason is you don't have many cation exchange sites to hold that magnesium in place. A clay can have a very high cation exchange capacity, 80 to 120. Now, that's a lot of sites, and basically that's a good thing, but you can have too much of a good thing. You can have too high a cation exchange capacity. You also need good physical structure to the area that you're trying to grow the grass on. If you have a heavy clay, you're not going to have very good drainage. And when it's wet and they're playing sports on it, they're going to tear it to pieces. So you need a good balance. At 180, 90, 120 is not necessarily a good thing. That's too high. Organic matter has a very high cation exchange capacity, 500, 150, 250, 500, very high cation exchange capacity per unit weight. So when we build a sand-based system, we pay a price because we have a low cation exchange capacity and usually a low moisture holding capacity. We can put some organic matter in there, like putting some peat in it, and we can boost the cation exchange capacity and the ability of that area to hold nutrients. But we can overdo that too. You can put too much organic matter in there. So too much is not necessarily good. What do we like to see when we pick up a soil test form? 25 to 30. 25 to 30 is what you'll see in a good clay loam soil like we have in the Midwest. That is the right physical characteristics usually for growing grass, and we have enough cation exchange capacity to hold the cations in place. So 25 to 30 is good. Does that mean you can't grow grass and other cation exchange capacities? No, you can do that, but if you've got 25 to 30, you're lucky. I see a lot of areas in my part of the country that will have 25 to 30, like a golf course, 25 to 30 on the fairways, 2 on the sand green. So it can vary a lot by location, and that has a lot to do with your nutritional program. A sand green, a sand sports field, they're usually going to start out very low. Like I said, I'll see 0.5, 0.8 cation exchange capacity. That's extremely low cation exchange capacity. Over time, it tends to increase. I had a student do a study on this a few years ago where he had good soil test records from a number of areas, and then he followed he spent 2 years on this, so he couldn't follow it for years and years, but he found areas that were 10 years old and 15 years old and 19 years old, and he could compare the soil test at the time of construction to the soil test several years later. And what you'll see is that cation exchange capacity tends to go up in time. It'll start very low out. It'll start out very low initially. And then because roots are dying in there, you're getting more organic matter. You're probably top dressing. You get wind blowing material in there. You'll get an increase in cation exchange capacity. And that also affects your fertility program. Magnesium can very well be deficient in the grow-in process. A couple years later, as the cation exchange capacity builds up, you change your fertility program, you'll usually have enough. All right, I said I would tell you what that chemical term is. What is a milliequivalent, or an MEQ? And again, on the top of the column, they'll have MEQ per 100 Gs. MEQ is per 100 grams. A 1 milliequivalent is 6.02 times 10 to the 20th power. Now, what do I mean 10 to the 20th power? There are 20 zeros behind that. So 1 milliequivalent in the soil is 602 billion trillion, whatever that number is. It's a very large number. These are very, very tiny, but 1 is still not enough. So that number is not enough for plants to grow in most cases. We'd like to see it higher. We'd like to see 8, 10 in a sand area, and 25 to 30 in a clay loam soil. Okay, again, the different areas, the type of soil you have is going to have a huge difference on your cation exchange capacity. I can tell right away when I pick up a soil test form by looking at that first line what kind of soil I'm dealing with. If I've got a 2, I'm dealing with a sand soil. If I got 25 or 30, I'm dealing with a clay loam soil. All right, the second column, or the second line that you find on the soil test is usually pH. Now that is written with a small p and a big H, and it normally drives my computer crazy because it doesn't like me putting a little p and a big H. In fact, every time I do this, it'll auto-correct me and it'll make that a capital P. It is a small p and it is a big H. What does the H stand for? The H is hydrogen. I mentioned hydrogen is a very important element to us in the soil, even though we don't normally think about it and we don't fertilize with hydrogen. Hydrogen is very important to us from a nutritional standpoint. The P is potential. It's a mathematical term, and it's a very complex mathematical term. As you'll see in a minute, it kind of bends your mind when you look at what it means. But it has been simplified down into a form that we can use, and we can predict things from the number that they give us. And again, what they'll give you is pH, and they'll give you a number beside it. Now, when we measure pH, again, we get a number, but it's a very complex number. First of all, the pH scale ranges from 0 on the left to 14 over there on the far right side. Right in the middle is 7, and 7 is the neutral point. Okay, it's neither acidic nor is it alkaline. And we do usually like to be around that 7 pH, but we're not always there. Now, you would think if you're developing a scale that is going to measure something, and we're measuring the amount of hydrogen that's in that soil, that you would have a bigger number being more hydrogen and a smaller number being less hydrogen. But that's not the way it is. With the way that pH is calculated, it's an inverse scale. It's flipped over. And as we go down from 7, we have more and more hydrogen. So our number is actually getting bigger as we go down. As we go up, we have less and less hydrogen. So it's just the opposite of what your mind would tell you. Your mind would tell you bigger number, more hydrogen, because we're measuring hydrogen. It's just the opposite. Okay, so remember that. And 2, it's a logarithmic scale, meaning that everything is based on a factor of 10. So if I go from 4 to 5, that's a factor of 10. That's not 1 unit, that's 10 units. If I go from 4 to 5 to 6, that's 100. And 4 to 5 to 6 to 7 is 1,000. So everything goes up and down on a factor of 10. So to move up and down that scale takes a lot. It takes a lot to move that scale. And that's what we're going to talk about here in a few minutes when we get into modifying the pH. We got to put a lot of stuff down usually to modify. Okay, but remember that 7 is the neutral point. As we go down, we've got more hydrogen. As we go up, we've got less hydrogen. So what? Why do we care? Why do we put CEC on that soil test and then pH? Because it tells us so much about what cations are on those cation exchange sites. If I have a soil with a low pH, like a 3, 4, 5, that means that I have a lot of hydrogen on the cation exchange sites. By default, if I have a hydrogen on a cation exchange site, I don't have a calcium. I don't have a magnesium. I don't have a potassium. I've got a hydrogen there. So that tells us a lot about the nutritional status of that soil. If I can just have pH and CEC, I can tell you a lot about the nutritional balance that's in that soil. I can tell you about the trouble you're going to have with grow-in and the type of fertility program you have to have. Now, we still need other information, so we measure the cations and the other nutrients in the soil. But these first 2 numbers tell you a lot. If I've got an acidic soil, I've got a lot of hydrogen. In very acidic soils, you'll get into aluminum. I've had a few people over the years in international seminars from some of the island courses in South America and areas like that. They have lateritic soils down there that have been weathered for many, many years, particularly in the tropics, and they can have a very low cation exchange capacity. And you get into aluminum and hydrogen on the cation exchange sites, they have real serious nutritional problems with these soils. Now, as you go up again above 7, you have more calcium, more magnesium, and more potassium. So your mind says, well, that's good. I need calcium, hydrogen, I need calcium, I need magnesium, I need potassium. So that's a good thing. However, again, too much of a good thing is not a good thing. So if we get too much calcium, too much magnesium, too much potassium on the cation exchange sites, we get an imbalance. We've got to have some hydrogen, we've got to have some calcium and magnesium, and you have to have a proper balance on those cation exchange sites. And when you get out of balance is when you run into a series of nutritional problems. Now, notice I've got an 8.2 here. And that's kind of a magic number to me. I see soil tests all the time with 8.2. Anybody know they got soils with an 8.2 pH? Pretty common, particularly in the Midwest. That tells me that that is a calcareous soil, that it has calcium carbonate in it. Calcium carbonate is lime, and part of the structure of that soil is actually lime. It's calcium carbonate. Now that means that they are pretty highly buffered soils, and I'll explain buffering in a minute, but they lock in at 8.2 and they don't want to change at all. Okay, so 8.2 is kind of a magic number. If you've got higher than 8.2, and when I worked in Colorado for a while, and it was pretty common to have very high pHs. I had 10, 11, 11 and a half on some of my greens on the golf course, and I had a lot of sodium in the water. So if you get a lot of sodium on the cation exchange sites, you're probably going to have a very high pH. So if you get into that 9, 10 range, that tells you probably got sodium. Okay, but again, you need a good balance. That's the key word. Now it's kind of hard to see this from the back. I have it in the textbook if you want to look at it in more detail. But what this is a listing of the nutrient elements that are most important to us from a fertility standpoint: phosphorus, potassium, sulfur, calcium, magnesium, and the availability at different pHs. This is pH 7 here in the middle. This is the neutral point. This is 10 over here on the left and 4 on the left, 10 on the right. So this is the range that most soils will come in. Now, the wider the line up there, the more available is the nutrient element. And the narrower the line, the less is available. Okay, so let's look at a couple of these. Calcium and magnesium, right there in the middle. Okay, notice that when we get in this pH range, about 6.5 to 7, the line is pretty wide. What happens as you get down into the range of 5 and 4.5? That line gets narrower and narrower. Why is that? Because we have a lot of hydrogen on the cation exchange sites. And again, by default, if I have a hydrogen on a cation exchange site, I don't have a calcium, I don't have a magnesium, I don't have a potassium. So again, when I look at that number, it tells me a lot about the fertility. So I'm probably going to have problems with cations like that. And I mentioned magnesium earlier. If I don't have enough magnesium, my grass is not going to get green. It's part of the chlorophyll molecule. And it's very common in the grow-in of a sand-based system that has a low pH. And I'll see some of these. I've got a 0.5 CEC, and I got a pH of 5. Okay, I can tell you almost for sure that you're going to have a magnesium deficiency in that soil. You've got to put down some Epsom salts or some kind of magnesium-containing material to get that grass to kick in. All right, so notice calcium and magnesium, they're right in the middle up there. They're wide, and through the 7, 8, 9, it means you got a lot of calcium and magnesium. However, out on the right-hand side, above 8.2, notice how calcium and magnesium get thinner again. There's less and less. Who can tell me what's going on there? Why are calcium and magnesium, why is that line thinner and thinner up there? What happens above 8.2? Sodium. Okay, so if you've got, that tells you that you've got a lot of sodium on the cation exchange sites. Just like with a hydrogen, if I have a sodium on a cation exchange site, by default, I don't have a calcium and magnesium. So it's taking up those cation exchange sites. So again, it tells you a lot about the availability of these nutrients. Now, so you'd say, look at this, you'd say, well, God, I got a lot of calcium and magnesium down through this range. Why would I worry? Look at iron right here in the middle. Iron is, it's available to the plant at about 6.5 to 7, but as soon as you get above 7, it changes its valency, and the plant can't get it as easily, and it's less available. So I've got a lot of available iron down here in the acidic range. However, when I get into the higher pH range, I get iron chlorosis. The plant just doesn't seem to want to function, and it's yellow, and I got to put some iron in there. And that usually happens at a high pH range. There's other trade-offs, manganese, copper, zinc, although they're usually involved in such small amounts that we don't worry much about those. But there are nutrient elements that are more readily available in the acidic range. There are nutrient elements that are more readily available in the high pH range, the alkaline range. And to get a good balance, we'd like to be down here in the 6.5 to 7 range. That's where we've got the maximum availability of most of these elements. So if you're blessed with a soil like that, and a lot of the soils in my area are about 6.7, so they got just that right balance, but that's not the case with most of our soils that we're dealing with in the turf industry. In fact, we'll take the soil like that out and build it out of the calcareous sand, and now we've got a pH of 8.2, and things change a lot. All right, so I have a low pH. I've got a pH of 4.2, and that's a problem. Okay, I'm probably going to have some nutritional imbalances there. How do I bring that pH up? All right, and the answer to that is generally liming. If you go in the show tomorrow, you will find booths that will sell lime to you. And lime, the function of lime is to bring the pH up. What is lime? It is calcium carbonate, chemically, calcium COC3. If you're taking notes, write that down, because I'm going to talk about calcium sulfate in a few minutes. Very similar material, but its chemistry is different and it has a different function. So if I'm going to bring my pH up, I'm going to buy calcium carbonate or an equivalent. What does lime do? Lime raises pH. And ever since I went to Iowa almost 40 years ago, I've always had to put a slide in the talk about lime raising pH. And the reason I have to do that is because a lot of people in my area came from a farming background. I grew up on a farm in north central Iowa, and at age 10, if you'd have asked me what lime is, I would have said it was this white stuff that you put on the soil and it's good. Okay, you get more corn if you put lime on, and that's fixed in a lot of people's minds there. So lime is a good thing if you have the problem that lime solves. So if I have a 5 pH, I'm going to lime. I'm going to bring it up into the proper range. However, I'll run into a lot of situations where the pH that I look at in the soil test form is 7.5, it's 7.8, it's 8.2, and people are liming because lime's a good thing. And many times I've visited areas. I went to a big insurance complex with acres and acres of lawn a couple of years ago, and they've got a 7.8 pH, and they're buying lime. And I said, well, why are you buying lime? Well, lime's a good thing. Lime improves the grass. Okay, lime is a good thing if you have the condition that lime solves. Lime is not a good thing if you have already too much lime. Your pH is too high. So you've got to have the condition that lime fixes. Now, what happens when you put lime down? And this is true of calcium in general, and there are other things other than calcium carbonate that we can do this with, but if you have calcium, remember that calcium is divalent. It has 2 of these positive charges. Now, we have a soil that has too much hydrogen on it. It's got hydrogen in most of the cation exchange sites, and we have a low pH. That's the definition of it. So we put some lime on, the calcium and the carbonate dissociate, and the calcium with its 2 positive charges can knock off 2 hydrogens. And over time, and this takes some time, it's not magic and happens overnight, but you start putting some lime down, and little by little, the calcium begins to take over the cation exchange sites. Now, if you need a balance again, and you don't want to just, if you overload it with calcium, which you can do, you can over lime, and you've got all calcium on the cation exchange sites, you got a problem. Okay, so now you've caused an imbalance on the other side. So you need to do this with your eyes open and taking good soil tests and get a balance. So we need calcium, and calcium is the cheapest and quickest way to do this, but we also need some magnesium. We also need some potassium. We need ammonium. We need some hydrogen on there. We can't go too far. So we're trying to attain a proper balance on the cation exchange sites. Anyone here use dolomitic lime? I got some hands on that. Dolomitic lime is a calcium carbonate and a magnesium carbonate, and that's a great material if you have a low pH soil and you have a deficiency of the 2. That'll give you some magnesium along with calcium. Very, very popular material in some parts of the country. But what we're trying to do is regain that balance of cations on the cation exchange site. Line number 3 on a soil test form, and this one's confusing to a lot of people. I've had a lot of calls on buffer pH over the years, and people will call up and they'll say, well, yeah, I know what CEC is, and I know what pH is, but the third line, buffer pH, sometimes they put a number on it, and sometimes they don't put a number on it, and they don't tell me what the number means. Okay, so what does buffer pH mean? And again, that will usually be the third line at the standard soil test form. It's got CEC, it's got pH, and the third line is buffer pH. And then notice on this one, it's got some dotted lines where they didn't even test for it. And that's confusing to people. Well, they tested on some of my areas. This is golf course greens. They tested some greens and they didn't test other greens. So what the heck's going on with buffer pH? First of all, what is buffering? You can look up buffering in a standard dictionary and it'll give you a definition. It is a resistance to change. And we use this term a lot all through the chemical sciences and in everyday life for that matter. If you take aspirin and take a lot of aspirin, it can cause an acidic reaction in your stomach. In fact, aspirin can burn a hole through your stomach with acid. So it's the same kind of chemical reaction going on in there. But you can buy buffered aspirin. Bufferin is a brand name, and it is buffered to keep the pH from changing. How do they do that? They put calcium carbonate in it. Same kind of chemistry. They don't want too much of an acidic reaction in your stomach. So buffering is a resistance to change. Now, way back before I was born, and I've tried to chase this down because I've got this in my textbook, and I wanted to cite the origin of it, but I've never been able to find it. Soil chemists way back in the 1920s and 1930s had a problem. And they were developing all of these concepts. They were developing CEC and test for it. They were developing pH, and it had an inverse scale, and it was just really hard to understand. So they said, how can we make this straightforward enough that people that don't have a background in this can figure it out and use it? And somewhere along the line, someone came up with this idea of using tires and tire pressure to explain buffering. And I've never seen a better explanation of what the concept of buffering is. Okay, so we're going to forget about soil pH here for a minute. We're going to think about tires and pressure testing. Okay, let's say you got a bike tire, one of those little narrow bike tires, and you pump it up to 50 pounds. Okay, you can do that pretty quick. You put the pressure thing on there, and boom, it's at 50 pounds. Okay, now we got a big old tractor tire next to it. Now that's pretty high pressure for a tractor tire, but for the sake of argument, we pump that up to 50 pounds. So I take the pressure tester, I put it on the valve stem over here, and it's 50 pounds, and I go to the tractor tire and it's 50 pounds. Now, let's say I go over here to the left and I put my finger on the valve stem and I let 10 seconds of air out of that bike tire. What's going to happen to the pressure? It's going to drop like a rock. Probably going to go from 50 to 30. Okay, now I go over to the tractor tire, it's got the same size valve stem on it. I put my finger on there and I let 10 seconds of air out. What's going to happen to the pressure of that tire? Maybe going to go from 50 to 49 and a half. Why does it not change? Because it's buffered. It's very resistant to change because of that huge volume of air in it. The tractor tire takes a lot of air in to build the pressure up. It takes a lot of air out to let the pressure down. Whereas the bike tire, the pressure goes up very quickly with a little bit of air, and it comes down very quickly with a little bit of lack of air. This is just like soil testing. So now let's go to a pH of the soil. I've got 2 beakers of soil up here, and I dip the pH meter in it, and this one is 5, and this one is 5. Okay, so it's just like a pressure test. They read the same, and they can look the same. However, what I'll find is that if I want to bring the pH up to 6.5, this one may take a few hundred pounds of lime per acre to do that. This one may take a few thousand pounds of lime per acre. And that's what buffer pH is measuring. It's measuring the resistance to change in pH, and it's telling me indirectly how much lime I need to apply to bring that pH up. And that's a very important issue because soils can vary a lot. If I have a sand soil with very few cation exchange sites, it doesn't take much calcium to replace those cation exchange sites and bring the pH up. On the other hand, if I have a muck soil, a heavy organic soil, and it has a pH of 5, I've got to put millions and billions and trillions of calciums in there to build that pH up, and it can vary a lot. So that's what that buffer pH is about. So how do I interpret a buffer pH? And that's a question I've got a lot over the years. So when I did the first edition of my textbook, I put a buffer pH table in it. And in the soils chapter, you will find a buffer pH table that you can take that number from a pH test and you can determine how much calcium carbonate you need. Notice that it varies a lot. Now, this is a complex table here. It's 2 inches, 3 inches, 6 inches, 8 inches. But notice the difference in soils. Some can take as little as 200 pounds per acre. Some may be 10,000 pounds per acre. So it really makes a big difference in the buffering capacity of the soil. And that's what that test is measuring. So it is not really a pH number. It looks like a pH number directly, but it only has meaning if you read it against one of these tables. Now, today, too, you can go to the internet. You could Google buffer pH table and you could come up with one. So they're pretty easy to get a hold of today. All right, we talked about calcium carbonate. Calcium carbonate has the function of raising pH, and it's a very good thing if you have a low pH. But if you go on the show again, you're going to find booze that have calcium carbonate, which is lime, and they have gypsum, which is calcium sulfate. They're going to look alike. They'll be a light, fluffy powder, and they both contain calcium. However, there's a big difference in it. Calcium sulfate is not a liming material. Okay, now that doesn't seem to make any sense. Why, if I put calcium sulfate on, I'm putting calcium on, why doesn't that bring my pH up? The answer to that is in the sulfate. When you put calcium sulfate in the soil, it reacts with hydrogen, the sulfate does, and it forms H2SO4. What is H2SO4? It's sulfuric acid. So sulfuric acid is trying to bring your pH down, the calcium is trying to bring it up, and you've got a neutral effect. So if I got a low pH, I don't want to grab gypsum to bring the pH up. I want to grab calcium carbonate. Now, the gypsum is very important to us in soil structure. If you've got good soil structure, if the fine particles of the soil are aggregated, they're going to come together and you're going to get proper drainage. However, where you have sodium in the soil, you hit a sodium aquifer, you're by the ocean, you've got salt on roads and that sort of thing. Sodium is a cation, and it'll begin to replace the other cations in the cation exchange sites. When it does that, it disperses the soil. Sodium has a very high hydrated size. You'll read that in the books. What does that mean, hydrated size? Sodium is a little tiny ion, but when you get water around it, it gets really big. Calcium, on the other hand, is a large ion, and it doesn't get a lot of water around it. And notice that calcium has 2 positive charges, sodium has 1. Okay, so if we start watering with water that's high in sodium, little by little, the sodium will begin to replace the calcium and other elements on the cation exchange sites. Calcium is monovalent, so it takes 2 big sodiums to replace 1 calcium. And as this happens, as you water with water that's high in sodium, you get a dispersed soil. You had soil with good structure, now you have soil with very bad structure because the large hydrated size of the sodium blows your structure apart. If I have that condition, I need gypsum, calcium sulfate. And why calcium sulfate? Because the chemistry is such that the calcium, and remember this is 1 little calcium with 2 positive charges, will come in and knock 2 big sodiums off, and then the sulfate will react with the sodium, and sodium sulfate is soluble, and you can leach it out of the soil. So that is the function of gypsum. You don't want to grab it for liming. If you got a sodium problem, you need gypsum and to restore that structure. Okay, I think I'm running out of time here, so I want to leave a little time for questions. Acidification. Now, we talked about being on the bottom side down here. I get a soil test, and it's 5.2, and I want to come up. And I can do that relatively inexpensively and relatively easy by using lime. Calcium carbonate with time at the right amounts will bring that pH up to 5.2, 5.5, and eventually I can get it up in the range of 6.5 and 6.7. And I balance my fertility program out. I can create a very good growing media for grass. Now let's say you're on the other side of the scale up here. You're at 7, 8, you're at 8.2 where you've got calcium carbonate in the soil. Or you're very high with sodium. Now if you've got a very high pH with sodium, you need gypsum. And gypsum will help bring that pH down to 8.2. But we're talking about where you got normal conditions, you don't have a lot of sodium in the soil, but you got a high pH. Okay, so I want to bring my pH down into that proper range. How do I do that? If you go into the show and you ask the people who are selling these materials, I've got a high pH, I want to come down, how do I do it? They're going to tell you sulfur. Okay, and that can be the right answer, and in some situations it's not the right answer. So that's what we're going to get into. When is it practical to lower the pH with sulfur and when is it not? Sulfur, first of all, is an essential element. Okay, so we need sulfur in fertility programs. Usually, though, we have plenty of it in the soil. It's also sold as an acidifying agent. So you can buy sulfur as a nutrient, or you can buy sulfur to acidify your soil. Sulfur deficiencies are very rare in turf areas. You can find it, but in most of the United States, we get plenty of sulfur in from the atmosphere. Okay, we burn high sulfur coal in the west, and it comes up in the atmosphere, and when the rain comes down here, it brings sulfur to us. We burn high sulfur coal in the central part of the country. It lands on the northeast, and it causes over-acidification. You can get fish kill and that sort of thing because it's too acidic. Okay, so we get a lot of sulfur in from the atmosphere. In Iowa, we get 12 to 15 pounds per acre per year of sulfur in from the atmosphere. So in most parts of the country, you're going to have plenty of sulfur that you don't need it as a fertilizer element. So we're usually not buying sulfur as a fertilizer element. We're buying it to acidify. All right, acidification. It is true that if you put sulfur on the soil, there are microbes, thiobacillus, that will react on that, and they will form H2SO4. What is H2SO4? It is sulfuric acid. So if I put flowers of sulfur on that soil, it will with time form H2SO4, and theoretically, that should bring my pH down. So if you ask somebody, how do I get a pH down in my soil, they'll tell you, well, sulfur. And that's kind of true, it's kind of not true. It depends on the buffering capacity of that soil. Some soils that have a high pH are so highly buffered that you could put sulfur on them forever. I have a research green at Iowa State that has a lot of calcium carbonate in it, and I've done calculations on it, and if I put down the most sulfur I could put down per year, it would take me 1,500 years to bring the soil pH down. So it is that highly buffered. And that is what you've got to watch out for. Now, the soils that are highly buffered, that resist change in pH greatly, are those that have calcium carbonate in them. We call these calcareous soils, and they are very common in many parts of the country. You get into the eastern United States, we usually don't see that. Usually the pH is a little bit low. As you get into the northern Midwest and the West, you've got a lot of calcareous soils. A lot of our sands in the Midwest are calcareous sands, and that's why I see so many soil pHs with 8.2. If I got calcium carbonate in there, it's going to be buffered at 8.2. Okay, so again, I want to bring that soil pH down, but let's say that I build a new sand football field, and I take a soil pH test and it's 8.2. Okay, now that's pretty high. And really, I'd like to be down here in the 6.5 range, but is it practical for me to add sulfur to bring that pH down? The answer lies in the buffering capacity. This is that same picture I used for buffering capacity on the low end. On the high end of the scale, I should really have a bigger tire, tractor tire that's the full screen, because you can have such highly buffered soils that, again, it's almost impossible to change the pH. My sand green with only 20% calcium carbonate in it, I would have to add enough sulfur to form enough sulfuric acid to eat away the calcium carbonate in the media, and that would be 20% of the media, and then I could start lowering the pH. So not until I consume that calcium carbonate can I lower the pH. So that means that soil is very highly buffered, and again, I don't have 1,500 years to lower my pH. So we run into this quite a bit. Raising the pH is quite practical in most situations. Lowering the pH is often impossible in many situations. What do we care? Okay, what are the agronomic implications of a high pH? Can I grow good grass at an 8.2 pH? And the answer is yes. I can grow great grass at an 8.2 pH. In fact, I'm doing it. I have a lot of soils, a lot of sand-based soils that are buffered at 8.2. Now, I'm probably going to have some nutrient imbalances. What sort of thing would I expect? If I've got an 8.2 pH, I'm probably going to have an iron problem. I'm going to have iron chlorosis, and I have to adjust my fertility program accordingly. I might have a manganese problem. So if you have a 7, 8, and 8.2 pH, rather than trying to acidify, rather than putting all sorts of sulfur on there trying to acidify, you're fighting a losing battle. Adjust your fertility program. Sulfur's expensive. It's not worth the effort. It can be hard on the grass. Adjust the fertility program to meet the requirements of that high pH soil. And you can grow great grass on an 8.2 pH if you just do a little adjusting of the fertility program. And iron is going to be one of the key materials. I would probably get a micronutrient package in that case because some of the other micronutrients can be deficient. The moral of the story here on sulfur and acidification of the soil, sulfur can be a great thing. If you need it, use it. In the Midwest, we've got a lot of overemphasis on sulfur. And they run into this in the ag crops too. They'll have people selling sulfur. You need sulfur. You got a high pH, you need sulfur. And a lot of times this is going to areas where the soil is so highly buffered you could never change it. Rather than spend thousands of dollars on sulfur trying to bring the pH down, spend a few dollars on balancing out the fertility program. It'll make a lot more sense. All right, that's my slides. I got just a couple of minutes for questions here. Any questions? Yes. Yes. Oh, okay. Now you're getting into a very complex question. I was hoping somebody'd ask that. That's a great question. How about these liquid calcium products that, does that make sense to me? Now, boy, it takes an hour to answer that question, and I have another seminar on that, but that's a great question. Chemically, the answer is yes. Okay, so I'm buying a liquid calcium solution, and if I got a low pH, it's going to raise the pH slowly. Now, if you look at those solutions, though, and I've got another talk where it's same subject, but it's exactly on what you just asked. If I've got a liquid calcium solution that they want to sell me for $80 a gallon, and that's a lot of times they're $50, $60, $70, $80 a gallon, or I can spend a few dollars on calcium carbonate lime, I'm going to spend it on the lime. Okay, so that calcium can work the same way, but it's enormously expensive form of calcium. So I can do it a lot cheaper with lime. Now, the second part of his question was on they're selling lime, they're selling these high calcium solutions in high pH soils. Okay? No. Okay? I don't buy that. That is not something I would recommend. And I had a PhD student, Rod St. John, who did his entire PhD on that very subject, and we've got publications on it, and the stuff's in the textbook. They tell you that. You need calcium even if your pH is 7.6. No, you don't. Your root system is bathed in calcium carbonate. You're not going to get anything out of that additional calcium, and we were able to show that. So don't waste your money on calcium if your pH is high, and don't waste your money on an $80 a gallon solution if your pH is low. Use lime. So generally, they don't make any sense. Yep. Oh, surfactants, okay. He said he has a high calcium soil and a high pH. Now, that's usually not going to affect your drainage that much. So if you need a and then the second part of his question was on surfactants, so I recommend surfactants. I could find soils like that where surfactant's going to make sense. I could find soils where it doesn't. So there's kind of an independent question. But generally, yes, the surfactants, you get a lot of benefit out of them. Again, there's a lot of variation in them. You can waste your money on too expensive and that sort of thing. But generally, they're going to benefit. Now, if you got a really high pH and you got sodium on the cation exchange sites and you have a reduced drainage because of the disruption of the soil particles, then you need calcium sulfate. You need gypsum, and a wetting agent may help, but a wetting agent's not going to solve your problem if your soil is dispersed with sodium. Okay? Yes. Okay, how would I change the fertility program if I've got an 8.2 pH, and which I do? I got quite a few of those. Okay, I know from that slide I showed you with the availability of different nutrients that I'm going to have certain elements that are probably going to be in a lower supply than I need. And iron is number one. Okay, so I'm probably going to use iron. Iron will go out of solution very quickly in a soil like that, so you can't just put it on and build it up. You've got to apply it quite often. And when I was a golf course superintendent in Colorado, we put iron sulfate in everything we did. Every spray application, everything, because it only lasts a few days. So feeding it with iron is going to be a very important part of it. And then I would look at a good micronutrient package, because it can be other things in soils like that. And they're cheap. And just to be sure that I've got it covered, a good micronutrient program with liquid applications of iron on a regular basis. Yep. His comment is that there's a lot of different iron sources, and I've run into this too. In fact, I've done research with different sources of iron. A lot of difference in response and difference in how long they last. There are chelates of iron, and they're more expensive. Chelate, the word means claw, and what's happening in a chelate is you've got an iron over here, and the soil wants to take it out of solution very quickly, but they put a chemical around it that kind of protects it, and it lasts longer in the soil. So you may see a few more days out of a chelate, but it's not going to be like you get months out of a chelate, days out of a soluble source of iron. You might get 3 or 4 more days with a chelate, but in a lot of soils, particularly extreme high pHs, that's going to be important. So probably in your case, I'd say probably a good, expensive, but a good iron chelate material, and then maybe a micronutrient program every few weeks. EDTH is a chelating agent. It's one of the chelating agents for iron, and that's a good material. Okay, and particularly in the higher pH ranges where the iron will go out of solution very quickly. Okay, I saw a couple more hands over there. Did I answer everybody's questions? If I did, I only got 10 seconds left anyway, so thank you very much.